Welcome to the first video of our next unit in calculus. This is a unit on applications of integration, and specifically a unit that covers how to find area and volume of different features. And this video today is going to talk about how to find the area of a region between two function curves. To start off this discussion, think about the state of Colorado. If I were to ask you to find the area of the state of Colorado, what would you do? If you look at the shape of Colorado, geometrically it's rectangular, so if you knew the length and the width of the state, you could pretty much find its area. There's not too much guesswork to really think about there. But what if I asked you the same question and just gave you a different state, like the state of Virginia? Clearly, this is not rectangular. There's many different angles and sort of curved regions, boundaries of water and rivers and mountains, and it's just not very easy to figure out what the area is of the state of Virginia. So what does this all have to do with calculus? Well, what if we were to build rectangles or trapezoids across the state of Virginia to try to break up the region into smaller pieces, smaller sections? And then we could just add up the areas of the rectangles or the trapezoids to get an approximate value of the area of the state. Or, for another example, what about the state of Hawaii? Here's a zoomed in picture of the island of Oahu. And again, if I want to know what the area is, the land area of Oahu, I would not really know how to do that. It's not rectangular. It's not a perfect geometric image. But if I start to build rectangles across the island, find the area of each rectangle, add them together, I'm starting to get a good picture of an approximate land area of this island. So hopefully you're thinking about Riemann sums a little bit. And remember that before we knew anything about integration, we started our discussion about integration with Riemann sums. Here's one last example. This is a satellite image of Lake Ontario. What's the area? What's the surface area of Lake Ontario? It's a massive body of water. Well, again, think about building a Riemann sum across a map like this, and you can get pretty close to an approximation of the area of that lake. So it's with those ideas in mind that I'd like to look at this first lesson with you today, and it's how we're going to use integrals to find the area between two curves. So here's a page of notes that I wanted to share with you today in this video. To begin with, I want you to notice something about the coordinate plane. We have to be able to find distance in the coordinate plane. So if we're talking about vertical distance, then that would be the top minus bottom, or the change in a y dimension. A y coordinate minus another y coordinate would give me vertical distance. If I'm talking about horizontal distance on the coordinate plane, that would be right minus left, an x2 minus x1 right minus left position. So that's how we find distance, horizontal and vertical distance in the coordinate plane. That's going to become a crucial step as we build these integrals to help us find area. So here's what we're going to do. We're going to basically be presented with different regions of area to compute. Let's look at number one right here. I have a horizontal constant of just simply y equals 1, and then the bottom boundary is the function cosine squared. And the question is, well, how much area is in that figure? So remember that definite integrals allow you to compute area from between the function curve that you're given and the x-axis. But now that I have a different lower bound instead of the x-axis, I want to simply find the area from the function curve on top down to the function curve on the bottom. So it's going to be this sort of top minus bottom idea. So what I want you to do in number one, I'm going to come back to the formulas in just a moment, but to begin, take a pencil or a pen, and I want you to draw a sample vertical rectangular strip anywhere in the region from top to bottom. Mine's going to look like this. Now I'm going to call the thickness or the width of that strip just simply dx. A small little tiny width to that little strip. So it's not a line, it actually has area to it. It has a length and then it has a little tiny thickness or width. We'll call that thickness dx. Now the length of that strip, which would just be the top minus bottom, or simply 1 minus cosine squared. So basically, if I take 1 minus cosine squared, that's the length of the strip, and I multiply that by its width, which I'm going to call dx. That's going to give me the area of the one rectangular strip. But in reality, I actually want to have an infinite number of rectangular strips covering that region. And there's this idea of a little bit of a Riemann sum. But we now know that if I want an infinite number of rectangular strips, then that just simply means integrate. Well, let's figure out from where to where. The intersection of cosine squared and 1 actually happens out here at pi. So that upper bound is going to be pi. The lower bound intersection point is a 0. So you're going to start at 0 and integrate all the way up to x equals pi. So the bounds of my integral will go from 0 to pi. You might recognize 1 minus cosine squared as a trig identity. So maybe we want to write that as the integral from 0 to pi of sine squared of x dx, just to be simpler. You wouldn't have to, but this is a nice, simple way of writing an integral that represents the area of that region. Now, up here are the formulas. Let's write them down. There's actually two different ways to find area between two function curves, and I'm going to start with the way that I just showed you, and that's when we have vertical rectangular strips. Try to zoom in here so it sticks. So this is pretty important. We want to integrate from a to b, and those a to b bounds are bounds in terms of x. And then inside of the integral, I have the function, the top function minus the bottom function, because distance in the coordinate plane is top minus bottom. The dx is a small width. Make sure we have a dx on the integral. And I drew a picture here of my vertical rectangular strip just to remind me of the orientation of the rectangles as I build them across the region. It is possible to do horizontal rectangular strips. If we take our rectangular strip and we just twist it, rotate it so that it's now horizontal, I no longer have a top minus bottom situation, but my integral is going to come up, or is going to basically consist of a right minus left situation as I construct those bars. So the formula is going to be the same. I have an integral from a to b, but now the a and the b bounds are going to be in terms of y. And that means the functions themselves should also be in terms of y. Rather than saying f of x minus g of x, I'm going to say f of y minus g of y. It'll be a right minus left situation here. And then not a dx integral, but a dy at the end. So those are my two formulas. Just kind of a little skeleton map of how you would construct an integral to help you find the area between two function curves. I did number 1 for you. Let's look at another one here. How about number 2? Again, I'm going to start this procedure by drawing in the region, a sample rectangular strip. And by the way, I don't want to go horizontally here. If I draw horizontal strips, it's possible that I would never hit the upper function curve. I want to make sure that I'm always sort of bouncing back and forth between each function curve, top and bottom in this case. So here's my sample rectangular strip. Again, thickness would be dx. And it looks like if I go top minus bottom, I will have the 1/2 secant squared x function listed first in my integral. That is the top function. And then minus the -4 sine squared, but a double negative becomes positive. Actually, to avoid confusion, I'll just do this. Minus the bottom times thickness, or times the width, which is dx. And then let's add the bounds. The bounds go from -π/3 to +π/3. Again, x-axis bounds. And that's it. That's my integral. I could use my calculator to find the value and approximate the solution to a decimal point. But this integral is the written expression that represents the area between those two function curves. How about number 3? We'll keep on going. I'll do this one and then one other example for you before we close. Now, here it says we can do this one in 2 ways. And if you look at this, I have the function 1 minus x squared and then the square root function, square root of 1 minus x squared as well. And it looks like, let's see here, the y equals 1 minus x squared is the bottom function here. You can double check that. And then the upper function is the square root of 1 minus x squared. So let's go with this vertical strip right here. And if I go vertically, then my integral will be top minus bottom. So root 1 minus x squared minus parentheses 1 minus x squared. And then dx is the width. And the bounds would go from, it looks like -1 to +1, or I could double 0 to 1 because I have symmetric regions. So that's one way to do it. Another way to do it is to actually rotate your rectangle and make it horizontal. And I want to show you how that works actually in the next picture, the final example here. Number 4. So the problem with a vertical strip in example 4 is, once again, it's possible that the vertical strip might never touch the other function. You have to make sure that you hit both functions every single time with all of the rectangles. And that's not going to happen if I go vertically here. It will happen if I rotate and make this rectangular strip horizontal. If you do that, I can't call it a dx thickness, it's now a dy thickness. The width is a small vertical width, and the vertical width is going to be in terms of y. No longer is this a top minus bottom situation, it's a right minus left situation. So I want to know what the right function is. The right function here is x plus y equals 2. But again, I want to write that in terms of y, so I'll call that x equals 2 minus y. I want everything now in terms of y, right minus left in terms of y. And then this function here, which is y equals x squared. Again, I don't really want y equals x squared. I want that in terms of y as well. So let's call that x equals the square root of y. We have to write our functions in terms of y if you take your strip and rotate it horizontally. So how does that look now in my final answer? Well, the integral here will be right minus left. The right function is the linear function, so 2 minus y gets listed first. That's the right. Minus the left of square root y. Right minus left. Notice how I have no x's in this integral. The thickness, the width, is also in terms of y, dy. The bounds must also be in terms of y. So the bounds here, 0 is the lower bound. The intersection point up there is y equals 1. So we're going to go from 0 up, 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 all the way to 1 as we kind of stack these horizontal strips. So there it is. There's a horizontal method. If your strips go horizontally to map the region, you can also use integration in that manner to find the area. One really important idea here to note with all these integrals is that all must match. I have bounds, I have the functions, the bounds, the functions, and then the dy, I'll call that the width, the widths of the rectangles. The bounds, the functions, and the widths as you construct your integrals all, jot this down, they all must match. And by that I mean you should not have f of x functions and y bounds, or you should not have a dy width in the integral and x-axis bounds. They all must be in terms of x, bounds, functions, widths, or they all must be in terms of y, bounds, functions, and widths. So that should get you started with finding the area between two function curves. Use those formulas, build either rectangular strips that go vertically or horizontally, and then construct the appropriate integral to map the area. That's a great start to the lesson, and I hope this video was helpful for you today.